Okay, good morning. So let us solve the homework problems. This is the simple one, yes? This is just related to product principle, I mean, the sum principle and complement principle. But let us do it, I think, anyways. So the first question, consider the following expression. After multiplying, how many distinct terms will the result have? Okay, so we have to answer that question. Okay, so how is it related to combinatorics? Yes. So I have A plus B. I want to multiply it by C plus D. And I want to multiply it by E plus F plus G plus H. Yes. First of all, this is very clear that because these letters are completely different, you shouldn't be concerned about if after multiplications term can be combined. Because terms will not be combined, yes? Because they will be all different combinations of these letters. So they are not similar, so I will not be able to combine them. But how can I solve this problem using combinatorics? How do you think about the problem? Let me review things a little bit if you have forgotten. So how can you connect this problem to the product principle? Because if you look at the end, every term at the end of this expansion is a term with how many terms? How many coefficient, how many factors? Any term at the end is combined of how many letters? Is the question unclear? If you start multiplying, you will get a bunch of terms added to one another. I'm asking concentrate on one of those terms and tell me how many letters are involved in that one single term. Yes, 3. Yes, so for example, one of them will be A, C, E. Yes. Is that understandable or not? If you start multiplying them, you have to multiply this by that, find the answer, and when you found the answer, multiply this answer by that, and then you will get a bunch of terms. For example, if you multiply A by C, AC will be one of the terms involved in this expansion, and after the expansion of this is finished, AC will be multiplied by this one, for example, and it will continue AC by F and etc. So one of the terms at a very final stage is ACE. Yes, this is very clear. So every term in this expansion includes 3 letters. Okay, but one letter is definitely coming from the first pair of brackets. The other letter is definitely coming from the second pair of brackets. And the last one is coming from the last pair of brackets. So in principle, writing a term in this expansion is a 3-stage task. Yes? You can imagine that the stage 1 is what you can make a story out of it. Yes? What is the stage 1? The stage 1 is choosing a letter from the first pair of brackets. Stage 2 is choosing a letter from the second pair of brackets, and stage 3 is choosing a letter from the third pair of brackets. Yes? In how many ways a stage 1 can be done? In other words, in how many ways I can choose a letter from pair of brackets 1, 2. Yes? So the number of ways for stage 1 is what? Is 2. Now you imagine you do it in one way. What do I mean by do it in one way? It means that either you choose A or you decide to choose B and it is finished. Now you go to stage number 2. Stage number 2 can be done in how many ways? The number of ways that I can do stage 2 is what? Is again 2. But here you have to be careful. Is this number 2 independent of how stage 1 is done? Yes, this is crucial because if you really want to use the product principle, checking this independence is important. So yes, it doesn't matter. If I have chosen A in the first stage, I have 2 options for the second stage, either C or D. Even if I have chosen B in the first stage, still I have 2 options. So this 2 is independent how stage 1 is done. Now let us say a stage 1 and a stage 2 are done. I want to see how many ways I can do stage number 3. How many options I have for stage number 3? I can choose any one of them, so it means that I have 4 options. But again, you have to be careful about something if you want to use the product principle. Is this number 4 independent of how stages 1 and 2 are done? It is clearly yes. So it doesn't matter which letters, which one of these two you have chosen in a stage 1, which one of these two you have chosen in a stage 2, still you have 4 options for stage number 3. So it means that product principle is applicable. So the answer to the question mark is what? 2 times 2 times 2 times, so 2 times 2 times 4 is 16. So this means that I can choose 16 possible terms from multiplying these terms. So the answer to the question is 16. So, and I hope that you are not confused why we are multiplying, not adding them up, because if I want to do one stage and leave it, the task is not accomplished. If I choose one letter from here and I do not choose any letter from here or any letter from here, the task of expansion is not finished yet. Yes? So we have to do them one consecutively, one after the other. Is that clear? Okay, because this is very good, because somehow in the next lesson, binomial expansion, that we will study later, this way of thinking is useful. Is that clear? Okay, so let us now go to the question number 2. So question number 2, consider the following table. Yes, so that you can see on display now. We want to erase each of the numbers in this table and replace it with a smaller natural number. In how many ways can we do this? Assume that the set of natural numbers starts at 1, because some people say that 0 is also a natural number. To make sure that you're not confused, I have mentioned that assume that natural numbers starts from 1. Okay? So in how many ways we can do that? Let us do it on the board now. Okay, so the question is clear, yes? We have given a table 3 by 3. Every time we want to do this, we want to erase each one of these numbers and replace it by a natural number less than that number in that square. That is the target, okay? Okay, so I want to accomplish this task. So this task can be broken into how many stages? 9 stages. And then you need to give a story for it, yes? Stage 1 is what? You can say some sentence for it, because it is very important for your mindset. I'm not asking you to write every detail down, but this is the mindset you should have. Otherwise, a combinatorics will be a random topic, yes? So you need to understand. Okay, so if I want to accomplish the task, meaning erasing each one of these numbers in these squares and replace them with a natural number less than that number, it is easy to understand that I can break this task into 9 stages. Stage 1, let us write a sentence for it. What is a stage 1? Stage 1, cleaning the first number and replacing it with the number smaller than that number. Stage 2 means cleaning the second number and replace it by a number smaller than that number. Stage 3 is stage 4, etc. So this task finally can be accomplished, can be viewed as being accomplished in 9 stages. Okay, can you tell me how many options I have for doing stage number 1? The number of ways that I can do stage 1, meaning, what was stage 1? Cleaning this and replacing it with a number less than 3. And a natural number. According to the problem, natural numbers starts from 1. So how many options I have? 2. Because I can erase 3, I have 2 options. Either replace it with 1 or replace it with 2. So I have 2 options. Again, stage 2. How many options are available for a stage 2? 1, because I erased 2 and I have to replace it by a number smaller than 2, which is 1. But this is also important to convince yourself about that. Is this one independent of what I have done in the first stage? Meaning, is it independent of if I have chosen 1 or 2 here? Yes, I have only 1 option. And again, the same story. How many options I have for stage number 3? 3. 1, 2, 3. Because 4 can be erased, either being replaced by 1, 2, or 3. So I have 3 options. But this 3, is it independent of how stages 1 and 2 are done? Yes. So I think you can immediately understand the story. Yes? So the answer to question mark will be what? For this one, I have two options. For this one, I have one option. For this one, I have three options. Yes? The next one, 1. The next one, 2. The next one, 4. The next one, 3. The next one, 1. The next one. That's, yes? But telling this story to yourself for combinatorial problems is extremely important. Later I will talk about that, because you know that there are some proofs. Actually, it is called proof by storytelling. Yes, this is in combinatorics. I will show you. It is not in your book, but it is not above your payroll or whatever you say. You should be able to understand those stories. Okay, so 2 times 3, because I don't need to consider ones, 6 times 2, 12, 48, times 3 is how much? 144. Yes, double check again, 12, 24, 72, 144. Yes, that's correct. Any questions? Okay, so if I go to here, here option 144 is of course correct. Let us go to the next problem. Okay, consider the following set, the set of all natural numbers from 1 up to 10. How many subsets of A do contain numbers 3 and 7, but do not contain numbers 1, 2, and 8? Okay, it's a good and a standard question in the topic of combinatorics. I hope that you could do it yourself, but let us discuss it here on the board. Okay, so what is the problem? We have still, I mean, here we have enough space. So the set given to us is the set 1, 2, 3, up to 10. Okay, let us review things a little bit. If I ask you how many subsets are there, just this question, without any extra constraints, you already know it from set theory we studied. What is the answer? If I just say how many subsets are there? Yes? 2 to the power 10. Okay, but let us try to review why this is the case. Can you justify why there are 2 to the power of 10 subsets of this set? Okay, why is that? You remember we talked a little bit about that probably before, but you have forgotten. Again, if you want to use combinatorics to answer this, and here the product principle to answer this, you really need to tell a story to yourself. You need to say that, okay, what is your task? Your task is to write a subset. So task, writing a subset of A. This is your task. Okay, can you write a subset? Everyone can write a subset. Okay, if that is my point. If you really can write a subset, if you just think how your brain processes the information to write a subset, in principle, you should be able to answer the combinatorial problem as well. So this task, if I ask you to write a subset, you might write 1, 2, and then suddenly 10. Do you agree? This is one possible subset. But if I want to look into my head, how did I come up with this subset? How did I come up? You told me write a subset, and I just wrote a subset for you. But if you look closer, what happened inside my brain, probably I knew about the numbers there, and I started deciding about, do I want 1 to be there or not? Do I want 2 to be there or not? Do I want to be 3 there or not, up to 10? But of course, probably my brain did it very fast. Even I myself didn't notice. Yes? So, for example, I looked at 1, I decided, yes, how many options I had for putting 1, for 1. I had 2 options. Either I could choose 1, or I said, no, I don't want to choose 1. So I have 2 options for 1. But I decided to put it here, choose it. Then for 2, I did the same. I liked it for some reason, I don't know, even I'm not aware what I did it, but I decided to put 2 there. In principle, how many options I had for 2, for making a decision about 2, I could decide 2 be in my subset, I could decide, no, 2 is not going to be my subset. Is that right? And how many options I had for 3 in principle? Potentially, again, 2. I decided, no, I don't want to put it there. And actually, I decided not to put any one of those up to 10, and I decided to put 10 there. So writing a subset, which is my task, can be accomplished in the way that I am describing for you in 10 stages. Yes? I can say a story for stage 1. Stage 1 is deciding about the situation of 1, being in my subset or not being in my subset. So stage 1 can be done in how many ways? I'm just talking about this problem. Then we go back to the problem on the homework. So how many ways I can decide about stage 1? 2. Yes, what is the meaning of these 2? It means that I can choose 1 to be my subset, one option. I can choose 1 not to be my subset, the second option. Is that right? Okay, then I go to a stage 2. What is the story of a stage 2? Deciding the situation of number 2. How many options are available to me? How many options? Again, 2. Is this 2 independent of my decision in the first stage? Yes. It doesn't matter if I have chosen to keep 1 or throw it out. How many options I have for number 2, 2. Yes? So I hope that you agree that this can continue up to stage number 10, deciding about the situation of 10. How many options I have there? 2. Or again, is these 2 independent of how the previous stages are done? Yes. So this means that to write a subset, I have to accomplish my task. It means that I have to accomplish every stage consecutively one after the other. Is the product principle applicable? Yes, because at each stage, this number is independent of how the previous stages are done. So this means that the total number of subsets is 2 times 2 times 2 up to the last. How many 2's are involved? 10. So it becomes 2 to the power of. Is that right? So that is the reason why if I have 10 elements in my set, I have 2 to the power of 10 subsets of that set. Okay, so now let us go to the problem on the homework. So what is the problem on the homework? The same set is given to you, and you are supposed to write a subset, but you have more constraints now. You are obliged to put 3 and 7 there. So 3 and 7 should be there, should be chosen. And we have another constraint. What was that? 1, 2, and 8 should not be there, yes? Should not be chosen. This is the constraint. Okay, but can you see now we can solve the problem exactly the same way? Writing a subset is a task. I want to write a subset. That is my task. This task can be accomplished in how many stages again? 10. Yes, because I have to decide about these things. You can view it in this way, okay? So what I will do, I will say stage number 1 is deciding about if 1 is supposed to be my subset or not. How many ways I can do it? How many ways I can do it? 1. Because they are forcing me, you have to choose it. There is no other option for you. So stage 1 will be done in how many ways? In 1 way, because 1, 2, and 7, 1, 2, and 8 has to be in your subset. Okay, if this constraint is not there, that is up to me to decide if I want to choose it or if I don't want to choose it. I had 2 options, but now they are forcing me, you have to choose 1 there, okay? Okay. Or you can solve it a little bit easier. You can say that, okay, yes. You can say that, let me do it in this way, not to confuse you. Okay, so stage number 2. Yes, in how many ways? Tell me, stage number 2. In how many ways I can do a stage number 2? A stage number 2 is deciding about the presence or not presence of number 2 in my subset. How many options I have? How many? 1, because they are forcing me that you are not supposed to choose it. So this means that I do not have 2 options, I have only 1 option. Okay, so let us do this number like that. What is a stage 3? In how many ways I can do stage number 3? Choosing or not choosing number 3. But they are telling me you have to choose 3. So then how many options are available? 1. Yes? So every element can be either chosen or not chosen in principle, potentially 2 alternatives. But here they are forcing me to choose 3. So I don't have any option not to choose. I have to choose. Okay? So what is S4? S4? Just tell me. 2. Because there is no constraint about number 4. S5? 2. S6? 2. S7? S7, 1. Because I have to choose it. S8? I shouldn't choose it. Again, 1. S9? What is that? 2. And S10? What is that? It is also? Okay. So the answer to the question mark will be multiplication of these numbers. But you don't need to count ones. How many 2's are involved? 1, 2, 3, 4, and 5. So I have to multiply 2 by itself 5 times, which becomes 30. It's a very standard question in combinatorics. Please let me know, is that understandable or not? Okay, so remember, this is the way that you have to remember to count the number of subsets. Okay, but this means that is up to you to decide about presence or not presence of those elements within your subset. Potentially for all of them you have 2 options. You can either choose them or not choose them. But if they give you some constraints for some of those elements, then you have to adjust yourself with those constraints. Okay? So in principle, if you want to have a rule of thumb, you multiply 2 how many times? By the number of elements with no constraints. Yes, this is the rule of thumb if you want to do it faster. But anyway, we don't have to do it much faster. Okay, so here, this option will be number 32. Is that clear? Okay, so now let us go to the next problem, number 4. This is a better question. I don't know how many of you could solve this problem. So how many 3-digit numbers with distinct digits are smaller than 457? Okay, so you can, if you haven't worked on the problem, you can start working on it and I will have time to erase the board, okay? So try to think about the problem yourself now. Okay, any ideas? So hopefully you understand that this problem is not a problem that we can just use the product principle because there are different scenarios involved. So the way that I do it for myself, I will try to understand the problem. So let us try to draw some kind of Venn diagram, if you can call it Venn diagram. So this is the total number of 3-digit numbers less than 457. Okay, so let us say that in this box, I am writing all those numbers that I want to count, meaning a 3-digit number with distinct digits less than 457. Okay, so let me say that 3-digit number is a 3-digit number ABC. Do you remember in number theory we learned we put this line on it so that you don't get confused to read this as a product. A is a digit, B is a digit, C is a digit, because I want to have a 3-digit number. And I know that because these digits are distinct, A is not B, B is not C. None of them are equal. Okay? But can you imagine that I can break this problem into different categories? Or the word is probably, they cannot happen simultaneously. Okay? So one case is that I would say that, okay, A is less than 4. Because if this digit is less than 4, I achieve the goal. The number, regardless of what B is or what C is, definitely is less than 457, because if this digit is less than 4, this number is definitely less than. So I consider this one case. But is this the whole story? No, because it might be the case that A is what? A4. Yes? But still, I have the chance to make my number smaller than 457. For example, 452, or let me write it like this, 400, so let me write this 8, and then this one, for example, 3. Yes? This number is still smaller than that one, even though it starts with a 4. So some of those numbers that I am looking for really start with a 4, okay? But b is less than what? 5. Yes? One question is this: do you think there will be an overlap between the numbers here and the numbers there? Because this is important. Is it possible that a 3-digit number with that property will be here and here simultaneously? Of course not, because these numbers, I am choosing those numbers whose a is less than 4, and here I am putting those numbers whose a is exactly 4. So there will be no overlap, because thinking about not having any overlaps in principle is important. Okay, but is this the only scenario? Not yet. There will be one more choice. What's that? No, not just b equals to 5. A is 4, b is 5, but c is less than 7. Is there any other options available? Is there any other scenarios? No, these are the only ones. But again, is there any overlap between these parts? No, there is no overlap between. So it means that either, so the numbers that I am looking for can be categorized into 3 mutually disjoint parts. So if I know how many of them are here, let me call it N1. If I know how many of them are here, let me call it N2. And if I know how many are there N3, the answer to the question mark naturally is what? N1 plus N2 plus N2 by the sum principle. And for the sum principle, it is important that there is no overlap between the parts. Okay, so that's why I was thinking about not having any overlaps. Okay, now make the problem simple for you. Just concentrate on calculating A1. Okay? And if you don't mind, let me write all the digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, these are the digits I can use. But for this one, again, for solving this problem, I want to use product principle. So can you tell me what is my task only for this part? My task is to write a 3-digit number with distinct digits whose 100th digit is less than 4. Okay, so I can do it in 3 stages. Writing a number with 3 digits. Digits are distinct. This a is less than 4. So how many options I have here? 3. Yes, because first of all, I shouldn't go beyond 4. These are my options, but I know that 0 cannot be chosen here. So I choose one of these numbers. How many options I have? So stage number 1, I have 3 options here. But because the digits are distinct, one of these things that I have used should be eliminated. Okay? So let us try to eliminate, for example, this one. Okay? One of them is eliminated, is used here. Now, is there any constraint here? Yes, we are not, no, one is is not in my list. So how many options are left here? Every one of these numbers can be chosen here, because you see you don't have any constraints on B and C. Okay? So how many options are available here? Any number in this list now can be chosen. Do you agree with me or not? So how many options are there? 9. But because a repetition is not allowed, another one is gone. Okay, be careful. Is this 9 independent of my choice here? This is important, you know. It doesn't matter if I had eliminated 1, or if I had eliminated 2, or I have eliminated 3. One of them will be gone, still I will have 9 options available. So far this 9 is independent of how this is done. Okay, this is very important. Okay, now this is what is stage 2. Stage 3. So one of the other numbers are also gone. I don't know, let us say that 4 is gone. Okay, then how many options are available here? 8. Do you agree with me or not? Okay, so, and this 8, again, is independent of how these 2 stages are done. Independent of what you have done here and there, still you have 8 options available. Okay, I am not saying that the options are not affected. The options you have are definitely affected. The number of options are not affected by your choices. And that is important for the product rule. So I multiply them. Product principle is applicable. So what is that number? 260. Am I right? 9 times 8, 72. 3 times 70 is 210. And that one is 6. That's correct. Okay, so let us put everything back now. 1, 2, 3, 4. And now I go to N2. So this is your N1. Now for N2, how many options you have again? You have 3 stages, sorry. Stage 1, stage 2, stage 3. Okay? I have 3 stages. Okay, stage 1 is already decided for me. Because the middle one, A is what? 4. So it means 4 is reserved for here. So how many options I have? How many? 1. And that is number 4. So let me eliminate 4 from there. Okay? And now I go to stage 2. At stage 2, I have this constraint. Okay? So I have to be less than 5. But one of them is gone. Yes? So less than 5, E in principle should start from here, but 4 is used. So it is eliminated from my list. So 4 options are available. So I put 4 here. And one of the other ones will be gone. And again, you have to convince yourself, is this, yeah, this is of course independent because we haven't done anything here so far. But stage number 3, can you tell me how many options are available now? Stage number 3 is to decide about C. I do not have any constraints about C. So any one of these numbers can be in principle chosen for C. How many options are there? 1, 2, 3, 4, 5, 6, 7, 8, yes. So that becomes what? Is this 8 independent of how I have done the previous stage? Of course, yes. So the answer becomes 30. Yes? And now finally, I will go to N3. So N3, I have a stage 1, I have a stage 2, I have a stage 3. How many options I have for a stage 1? The stage 1 is already chosen for me. It has to be 4. So I have only one option. So let me write it again, 1, 2, 3, 4. So 4 is gone from my list now. Stage 2 is already decided for me. It's 5. So it's only one option. So that is also gone. Yes? But now, stage 3, C should be less than 7. I should be less than 7. But 2 of them are gone. 1, 2, 3, 4, and 5 is left. Agree or not? So it means that 1 times 1 times 5 is 5. So the answer to the question mark is 216 plus 32 plus 5. Yes? What will be the answer? 7. This is 3, yes. So what is this one? 250. Okay, so you see, some students think that they have to do things fast. Okay, because the answers in combinatorics are just one single number, somehow, I don't know, this is the feeling that you think you have to do things very fast. No, that's not the case. If you really want to master combinatorics, you have to be very patient, tell a lot of stories to yourself, think about every details. Because if you don't, if the problem becomes a little bit complicated, this is a very common mistake. People start double counting and things like that. For example, if you need to use the sum rule, you have to respect the prerequisites of the sum rule. So when I want to use the sum rule, I really have to convince myself that there is no overlap between these parts. Okay, so this takes time until you really master it. And even if the problem becomes 100, it doesn't matter how good you are, you have to think and go back to the principles and make sure that you're respecting every details in this one. So this number is 253. So that is, if you really could solve this problem on your own, it means that you really mastered, I would say, you really mastered the sum rule and the product rule. Okay, these are very ideas, simple ideas. Okay, so let us go to the next problem now. Any questions? Okay, so again, let us read this. How many numbers in the set 83, 84, 85 up to 211 are divisible by 2 but not by 3? Okay, so how we would think about this? I can give you a little bit of time, even if you have done it before, it doesn't hurt if you refresh your memory about it, okay? Okay, so have you thought about it? So I call this set A for simplicity. So how do you solve the problem? How do you think about the problem? I mean, drawing some Venn diagrams or some diagrams is a good tool, okay? So for example, I would prefer to, let us say that this rectangle represents the set A. So it means that the elements of this set is somewhere scattered in this rectangle, okay? And then some of these numbers are divisible by 2, some of them are divisible by 3, some of them are divisible both by 2 and 3, some of them are divisible by neither. Yes? So, do you remember we had in set theory, so let me call here divisible by 2, divisible by 2, and I want to draw another circle divisible by 3. Do you think there will be an overlap between these two, or I should draw them separately? Overlap, because there are some numbers divisible by 2 and 3 simultaneously, so it gives you the idea, okay, so let me write divisible by 3 like this. Yeah, you don't need to write them down, but you have to imagine it here. Okay, which part I am going to count? I am going to count the number of elements if this second constraint is not given to me, so I have to see how many numbers are there within the left circle. Everything in the left circle. But here we want to make sure that divisible by 2 and not divisible by 3. Okay? So this means that I am looking for which part? For this part. I want to know how many numbers are within this hatched area, yes, region. Is that clear? Okay, so then how should I count them? First of all, I don't know, if you don't mind, we can give them names in set theory language. So what is that set, by the way? Do you remember from set theory? The hatched region can be written in set theory in which way? M minus n. Do you remember that? Set theoretic difference, okay? So what I am asking you is to calculate the cardinality of m minus n. But this is not very hard to see, in the picture at least, that this becomes the cardinality of m minus the cardinality of m intersection n. Is that right? Because that is what you have. The number of elements here is the total number of elements in the first bigger set minus the element of these things which are here. But this is called m intersection n in the set theory language. So this is what you want to calculate. So you have to know this part, you have to know this part. Yes? This part is easy. What is the meaning of this part? The cardinality of the set M. What is set M? The number of these elements which are divisible by 2. So how many of them are there? The first one in your list is 84, because you want to have even number. The second number in your list is 86. And the last number in your list is 210. How many numbers are in this list now? These are even numbers divisible by 2 numbers from this list. So how can I know how many of them are there? Yes?
The biggest one minus the smallest one over 2.
That is a common mistake. Over 2 plus 1. That plus 1 is important. Do you remember? I don't know how many of you remember from Math 1C, arithmetic progression. So if you have an arithmetic progression, do you remember what is an arithmetic progression? An arithmetic progression is a sequence of numbers one after the other, so that every number is derived from the previous one by adding a constant non-zero number to the previous one. So that one is called the common difference. Yes? Up to the end. For example, the famous one is probably this one. You see? This is an arithmetic progression. What is the common difference? Every time I am adding 1 unit to it. But, for example, 5, and then 9, and then 13, and then 17, up to n. This is also an arithmetic progression, but every time, what I'm doing? I am adding 4 units at a time. Okay, so that is called an arithmetic progression. Is this an arithmetic progression? Yes. Every time I am adding how many times? How many units? 2 units. Okay? And then I just want to write the formula. The formula tells you that a number n is a number 1 plus n minus 1d. If you have forgotten, this is also, of course, in the formula sheet, but this is something you learned in Math 1C. Even if you haven't learned or completely forgotten, no problem. That's the formula. This is the formula that tells you what is the term number n. The term number n is a1, term number 1. How many D's are involved? Of course, n minus 1 D's. Okay? So now if I ask you what n is, so now you see I move a1 to the left, so it becomes an minus a1 is equal to n minus 1d. I divide by d. This is exactly what you told, yes? But this does not become n, it becomes n minus 1. So if you want to find n is what? N is the last term in my arithmetic progression sequence minus the first term divided by the common difference plus 1. This is the source of a lot of errors, so be careful about that plus 1. Is that clear? Yes or no? For example, if I say how many numbers are there in this set? How many numbers are there in this set? Of course, you say if 10 minus 1 is wrong, because 10 minus 1 is 9, and you already know how many elements are there, 10. One more. Be careful about that. So, let us answer the question for this one. How many numbers do you see in list? The last number minus the first number divided by the common difference. The common difference here is 2. But plus 1. This plus 1 is important. Okay? So what is the answer? Can you do it in your head? Okay, if I want to do it, if you don't mind, let me just divide. It is easier for me to subtract and divide. So this one is 105. If I divide this by 2, if I divide that by 2 is what? 42. And then everything plus 1. So what is, this becomes 64. Do you agree with me? Yes? Okay. This is the number of elements. So the first question mark is 64. But how can I count the number of elements here, exactly the ones which are both in M and N simultaneously? In other words, the number of elements in this list which are both divisible by 2 and 3. But we learned this in number theory. A number is divisible simultaneously by 2 and 3 if and only if the number is divisible by 6. So that is the interpretation. If I want to answer this question mark, this means that I have to count the number of elements that are simultaneously divisible by 2 and 3. We learned in number theory this is equivalent to saying that my number is divisible by 6. So again, I will do the same thing, but instead of having 2 involved as the common difference, 6 will be involved. Yes? So what is the smallest number in my list which is divisible by 6? 84 itself. Do you agree this is also divisible by 6? And then what is the last number in my list? The next one, of course, will be what? The next one will be 90. Yes, because we want to count the number of divisible by 6. And it will continue. This is important to know the last number in my list. What is the last number in this list which is divisible by 6? 210 again, because 210 is definitely divisible by 3 and divisible by 2, so it is definitely divisible by 6. Okay, but this time, what is the D? D is 6 at a time. So if I want to know the number of elements involved here, I have to do the same thing. 210, the last number in the list, minus the first number in the list, but this time divided by the common difference, which is 6, but again plus 1. Okay? But you were lucky if you didn't consider 1, because this 1 will appear here and there, it will be eliminated. So coincidentally, you will get the correct answer even without knowing the correct answer. Okay, so that's important. In this case, you will reach to the correct answer. So now what happens? This one divided by this, what is the answer? 35. Do you agree? And this one divided by that is 14, and then plus 1. So how many numbers are there? 22. Do you agree? Double check. Yes, that's correct. And now I put what here? 22. And then I subtract them, it becomes 42. Okay? So that is why, I don't know, if you haven't considered this one at the end, still you will get the correct answer, but that is a coincidence. Because 1 appears in both of them, and in the subtraction, it will be eliminated. So the number that you are supposed to put here is just 42. Okay, and then let us, any questions here? Understandable? So let us go to the next one. This was just designed for factorial, and these options designed from a little bit psychological point of view actually worked because many of you made a mistake in calculating the final answer. Which of the following options is equal to this product? 3 times 6 times 9 up to 30. Yes? So let me write it on the board. 3 times 6 times 9 up to what? 30. I want to write it in the form of factorial. What of these options? So you want to write somehow, because by looking at the options, you immediately realize that you have to do something with factorial notation. Okay, so let us go back to the board. So what do you do? So that was, I don't know, some of you made a mistake. Why? We'll see why. So how do you think about the problem? Because I need factorial, so I need a product of consecutive integers from 1, 2, 3 up to some point. Yes, this is what we know. By looking at the options, I want to make factorial involved. So that is very natural to think what product I can have from 1 up to some point, because that's the meaning of factorial. Okay? So this motivates you, might be, this is the mistake some of you made, 3 can be written as 3 times 1. Do you agree? But what can I write for 6? I can write 3 times 2. What can I write for 9? I can write 3 times 3. What is the next number in the list? It's 12. So what can I write? I can write 3 times 4. And I can continue until the very end. I can write 3 times 10. Do you agree or not? Okay? But if you, some of you, I think you made this mistake. You factored 3 out. You cannot factor 3 out, can you? Because there are how many 3's involved? So they are being multiplied. So this 3 multiplied by this 3, multiplied by this 3, multiplied by the final 3. How many 3's are there? 10. Yes? Because this is the first one, number 1. This is the second one, number 2. The third one, number 3. And that's the last one, number 10. So there are 10 3's involved. So this means that 3 multiplied by 3 up to 3, 10 times. And then what is left for me? 1 times 2 times 3 times 4 up to times 10. Okay, so this becomes 3 to the 10. What is the name of this? 10 factorial. So it was a good question, yes, but I tried to write the options in a way that you fall into the trap, and some of you did. Okay, so we have to be more alert. Okay, so this option is which one? The last one here in my questions. Okay, any questions? Okay, so we stop here. Thank you.